All right, here we go. So, first order of business is that I had provided p3.tar. I have made updates to a couple of the files. I found out that I had made some horrendous typos in them that would make things not compile. So go ahead and just grab a new copy, assuming you've already gotten a copy of p3.tar, grab another one and just overlay it over wherever you put the old one as far as extracting it. There's no new stuff, just modifications to existing files. Regarding what's missing from what I want in the project materials that are presented is the nice HTML kind of walk through the project and get it done. I'll be getting that done during spring break. Having said that, I did, as I said before, there was that file, what's it called? expressiongrammar.txt that's both here discretely as well as inside the tarball. You can actually get quite a bit done by looking at that. That said, I do want the nice formal write-up to be consistent with what you all have received previously, so that's forthcoming. Another thing that's forthcoming is the testing suite, that test directory that contains all the different examples for you to run through. I wanted to completely rework that. One of the problems with it in its existing form is, for instance, the very first test requires you to have it about 3/4 of the way done before you'd be able to pass that very first test. And I really wanted to make it so that you could work progressively on the project and get to test pass 1. Once you're done passing test 1, then you're able to examine what's going on in test 2 and so forth. I am not working into my timeline that you all are working over spring break. I feel fairly strongly about spring break being a break. Huh? Fair enough. So you'll have definitely have at least a week after our return to work on this project. That's also consistent with me not having quite all the finished materials there. So I think I owe you that at least. That said, I know that some of you like getting ahead of the game so that you don't have it hanging over your head. By the end of today, you should definitely have a big enough understanding of the workflow as far as the project development workflow that you could crank out a fair amount of this project over the break if you were inclined. Okay? So that's what I have on my agenda. Does anyone have any questions before we dive right in? Okay, then let's, yes?
Still uses the same bin file from the other project, right? To run it?
The same make file. All those files, yeah. Your starting point for project 3 should be everything in project 2. So create a project 3 directory, copy everything into except for the test directory, copy everything into P3, and then grab that tarball and extract it over. The order doesn't matter. You could extract the tarball first, which would create P3, and then copy all your old stuff into it. There's nothing being replaced. They're just new files being added. So to refresh what I'd thrown up there last time, we talked about expression trees, and that the key to the expression tree is that regardless of what kind of thing or where it is on the expression tree, every single one of those things that you would ever find in the expression tree, you should be able to stare at it and say, evaluate. And as a result of asking whatever that thing is, wherever it is on the tree to evaluate, what you can expect to be given back is a constant. Now we're dealing with pointers here. Everything's in the terms of pointers. Let me also say regarding pointers, I had you using shared pointers for the stuff that we've done up till now, and I still advocate that, and where we can we will use them. Bison doesn't play very nicely with the shared pointers. So I had a choice of either adding a whole bunch of extra crap in there to make it work with shared pointers at the Bison level, or I would just, I don't want to say call defeat, but decide not to use use shared pointers and unique pointers for the stuff that's connected to Bison, and with that we'll just use good memory management practices. Okay. Anyway, so as a result of anywhere in that expression tree, you say evaluate, you get back a pointer to a constant. And what we're highly taking advantage of here is that idea of polymorphism, where it doesn't matter where the interface, meaning in this case the function called expression, is the same for every single class in this hierarchy. Let me bring some of that up. Let me actually look at expression.h. All right. So there's an expression class, which is this base class. It has that equals 0 for one of these functions, which means we can never create an expression object. We're going to derive classes from which we'll create objects. But the key here is that there's a function called evaluate. It returns a pointer to a constant object. And we can see an example of a couple subclasses here. There's one called binary operator. That one also is abstract. You never create a binary operator object. What you do is, if you're doing addition, you create a plus object. If you're doing multiplication, you create a multiply object, and so on for every binary operator in the language. Likewise, as this diagram implies, there is a unary operator class that's created, and from that, all of the operations that only involve a single operand. And that, there's no code provided for that. It's assumed that you'll write that yourself. And you should be have that pretty well in hand once you have coded up several of these binary operators. Looking at the constant side, again, the evaluate function returns a pointer to a constant, and this is notable in that this class, so let me look at the constant class, you'll see a whole bunch of virtual functions with equals 0. This class is abstract. You never create a constant object. You create objects that are derived off of constant. And looking at this diagram, right now we've gotten far enough into the GPL language, implementing it, that we have integer constants, string constants, and double constants. Okay? And now, let me rephrase what I said. No matter what kind of expression you have, you ask the thing to evaluate, you're guaranteed to get a pointer back to either an integer constant, a string constant, or a double constant. Now, interestingly enough, that does include integer constant, string constant, or double constant. Note that this whole part of the hierarchy is also derived off of expression, which means even constant objects have this evaluate function. So driving that home with an example, whatever, XYZ is. So I can say XYZ evaluate, and this is going to give me a pointer back to a constant. If some var A happens to have a 3 in it and some var B happens to have a 4 in it, then we would expect to get a constant integer object back that had 7 in it. Likewise, I could, what if I had This is all pseudocode, right? This kind of stuff's pseudocode, just to give us an idea of what's in it. Even if it's a constant integer object, I can ask that to evaluate. Why? Because all constant objects are inherited from expressions. Every expression in the class hierarchy has an evaluate function. So that's why we can do it. The question is, well, if evaluate returns a constant object and it's already a constant object, what in the hell does it return? And that is evident in, I think, constant.cpp. It returns itself. And so we have consistency across all expressions. Whether we're looking at the number 3 or some complex algebraic expression, I can be confident that if I ask that thing to evaluate, I will have in my hand a constant object at the end of it. And I didn't need to know whether or not there was a constant object there to begin with. I just blindly say evaluate, and now I'm confident I have a constant object. Once I have that constant object, I become very interested in what the value of that constant is. And so I don't know, again, once I call evaluate, I know I have a constant object, but I don't know which one of these 3 it is. I don't know whether it's an integer constant, a double constant, or a string constant. So all I can do is ask that constant, whatever it is, to please give me your value, and I have to say what I want it as. Now let me start down here as an integer. Actually, let me start up here as an integer. So whatever the expression is, I ask it to evaluate, and then I say, please give me yourself as an integer. And if it is an integer object, I'm assuming it is an integer object, then it'll just give me its data, which is an integer. So I would get, you'll note that the return type here is an integer. I can also ask this integer object, again, not knowing that it's an integer object, give me yourself as a double. And you'll note that the return is the same. This is C++ code we're looking at. What happens if you say double x equals 3? It assigns 3.0 to x, right? It'll do some implicit promotion of the type. So we're just taking advantage of that. And then finally, if this integer constant, I say, give me yourself as a string. Then what it does is it just simply converts that number to its string, ASCII string equivalent, and it gives me that. Okay. Now, the question is, how would I know whether I wanted to ask for, whoops, looks like I made a change here. There we go, S string. How do I know which one of these I want? And I will run through examples of where it's crystal clear which you want, but let me give you just a quick example here. String S equals 3. So we'll be running code. It will create one of these integer constant objects from this 3. And then I ask it to evaluate. It gives me itself. And then I say, give me yourself as a string. Why did I ask for it as a string? Because that's what I'm expecting to be on the right-hand side. That's how we know. And so really what the internal conversion is to do something like that. Semantically, it does something like that. And it has that single character in S. The final thing to note that we'll be looking at is there are times where things go awry. Int x equals. So through the processing through GPL.y, this will become a constant object, but it's going to be a string constant. And I'm going to ask for it as an integer, because that's what I'm expecting. And when I ask for it as an integer, I can come down here to the string type and see what happens when I ask for a string as an integer. And what it does is it throws an exception. And this here, what kind of thing is this right here? So this is what is the type of variable that this is? It's GPL type, right? You crack open GPL type.h and you have string, int, string array. You have that big laundry list of types. So this will throw an exception, and the information it will give us is what in fact the thing is. And that'll be useful to us as we'll see moving forward. We haven't talked very much at all about exception handling. I guess I should try and give, I need to make this as short as possible. So let's see, let me come out here. And what you generally do is you have what's called a try block, a catch block, and of course you'd have code before, and you would presumably have code afterwards. What you put in here are things that may possibly throw an exception. What you put in the catch block is what you do if an exception is thrown in any of this code, right? This could be thousands of lines long inside this try block. If anywhere inside here that throw is encountered, it will immediately bail out of where it was and jump into this block of code right here. And this is where you can do things based on that exception having occurred. The general strategy is you create your variables before the try block, and you do something like this. So you say character pointer, my string equals null pointer. And then you try to do something in here like my string equals get the name. And I don't know what get the name does, but let me go ahead and create it. It returns a character pointer, get the name, and somehow get the name. If something goes wrong, throw, and then it's up to you what you throw. There are actually some built-in exception classes in the language. Those are the reason they exist in the language is to give the standard library things to throw that are meaningful. For our purposes, it doesn't matter. Well, you saw that I was throwing GPL type. I don't want to bring GPL type into this example, so let me just throw a number. Doesn't matter. If I have sometimes you don't care the kind of thing that's thrown. You just want to know if it's thrown. This here is actually valid code. This means catch anything and everything that could be thrown, and you won't have access to the value of what was thrown. But it's kind of it's like the default branch, if you will, in a switch statement. It gets all the cases. In this case, if I am expecting an integer to be thrown, I can do something like the thrown value, and then I can do whatever I do in the catch. So here I set my variable. Note it's outside the try block. Why do I not have it inside the try block? And so let me actually continue and re-ask the question. I'm going to get rid of my bogus code here and see out a big was thrown. And then maybe I'll say that my string equals, and then I give it some default value. Now and then do interesting things with my string. So this is kind of the architecture of when you're using exceptions. So let me re-ask the question, why did I declare my string on line 13 and not between 14 and 15? It needs to be in scope. That's the key. If I declare it on line 14, it goes out of scope once I hit the closing curly brace on line 16. Okay, so to prevent that, you generally declare these variables before the try block. You try to do something, and then you go from there if something goes wrong. Okay. Now, again, the reason for, I touched on this last time, but the reason for throwing exceptions, and remember these are on functions like when I want to get it as an int, is there's no invalid value, there's no invalid integer I could possibly return to indicate an error. So this is my only recourse for saying that something went wrong and I couldn't convert it to an integer, is to do this exception handling mechanism. Okay, so let's go ahead and, I guess let me compile this. Let me see if I've got valid stuff here. So this is throwing an exception here. Let me throw let's do something interesting with my string. This seems quite interesting. All right. Let me compile it. And G++. I knew it was going to do that. So let me change that to a constant. Let me change this to a constant. All right, now let me get rid of the exception. So everything goes fine, and what I did was I returned toddy. And I'll comment that out. Okay, so you get different behavior depending on whether an exception was thrown. All right. Coming back to the project now. I can go ahead and hopefully I can make this thing. So I recall that because of some stuff we did, we get these warnings here. These warnings are going to be a little bit irritating for a while, but just keep. You want to look at anything happening either before or after. And your cue that you can ignore this is that it's giving you a warning about TID. So we ignore all the TID stuff. We can see there's nothing before them, and afterward it looks like just valid compiling stuff. Now I can go ahead and there's a test run. Let me clear the screen, get it at the top here. All right. GPL requires a file name. I want to take advantage of doing some simple testing by using this printf idea, and I want to create an integer x. I'll put a new line in there. I suppose a new line isn't mandatory, but I'm a creature of habit. So the issue here, again, is that GPL is expecting the name of a file, and yet I'm trying to pipe something in through standard in. So I use this nice Linux stub here, which is basically an entry in the file system that if you open it up and read from it, it's actually coming from standard in. So it's a nice way to fool GPL. Okay. I run it, and we get this right here. Note that this is hard-coded to 42, which is consistent with what we wanted in the previous project, defaulting all these to these certain values. Let me go ahead and clear the screen again. I'll do it again. This time I'm going to assign 99 to x. And once again, it's 42. Okay, so my first step in cracking this nut is to start adding stuff so that we can go ahead and assign 99 to x and get it to print out. Have 99 in the symbol table rather than that hard-coded value. So the first question is, where is 42 entering the grammar in GPL.y? Or excuse me, not that, the 99, right? So your parser is parsing this. It parses the int, the x, the equal to 99. Where is the entry point? Where is the first point where it's going to see the 99? So let me bring up GPL.y. So there's this optional initializer. We know, let me come down here, let me clear the screen, bring that back up. So taken as a whole, int is simple type, x is TID, an optional initializer is equal 99. But 99 enters the grammar before this point. Where does 99 enter the grammar? We can follow this backwards. I don't know how far we'll get. So optional initializer is an equal sign and then expression. Let me zoom in here. I would call this a little bit of a dead end in hunting the beginning of it for one reason only. That is, expression is the most common token in this grammar, and who the hell knows where we go with it, right? So following it backward, it's going to be difficult. Let's go the other direction, which is where does the 99 come in? How about, what if we look at GPL.L? Ah, yeah, right here. Yes, it's T T and constant. So it's this token. It gets scanned and pulled apart here by the flex side of things. It goes ahead and the semantic value of 99 is assigned, and then it returns this token. So this is the token we want to look for in GPL.Y. I do a search, and there it is. That's where it enters. Okay. Now the question. What I want to do is I need to start passing that 99 on up the chain until we reach that optional initializer point, right? So the first question is, what kind of thing is our 99, our T constant? An integer constant. We need to create one of those. So I'll say new integer constant. And let me go ahead and bring up, let me write that. Let's look at the constant.h file for a minute. My integer constant is right here, this code here. I'm going to construct it using this. And so I need to pass it the number to the constructor. $1. What am I assigning this to, though? This is floating in space. $, right? And now what we need to do is start traipsing this on up until we hit optional initializer. So this constant integer object is floating up till we hit optional initializer. All right. This is going to start the fireworks. Whoops, I need an equal sign there. This will start the fireworks, so let's not put it off any longer. Let's comment that out, and I'll type make. Let me zoom in here. All right. Again, you want to start looking at stuff before. Here's my first warning about TID, so I want to look at stuff before that. And I have it here, and it says primary expression has no declared type. Okay, this error is saying that it doesn't know what kind of thing this should be, what kind of token this should be. We saw this in the last project, but we only saw a little bit of it. Does anyone recall how you specify the kind of thing one of these is, one of these tokens? Percent type. Let's look. We did it. We did it for simple type in the previous project. So there's primary expression. I'm going to have that. I'm going to have percent type. All right. Now here's the next key question. What kind of thing will go there? So keep in mind, all of these are going to be assigning stuff to $, when we're done. So that's one candidate, certainly, as a constant pointer, right? Because we do have integers, doubles, and strings, and we'll have a similar statement for those. But yeah, so we're going to have like this situation where there's a variable and there's an expression, and in which case we've got to go all the way to the very top here. So it's an expression pointer that's being returned. And we can do this. We saw with polymorphism. You can take the address of any derived object and assign it to a pointer of a base type, right? A shape pointer, and it took a circle object or a triangle object, that kind of thing. All right. So I come here and I'll use my naming convention here, and that won't be too creative. We'll just call it an expression pointer. Now what's the next thing I need to do? I've created this out of thin air. Add it to the union. So remember, that's %union. So there's that part of it. And what kind of thing is it? There you go. Okay, try again. Make. Got some errors thereafter. Let's see if there's anything before. Here's my make, and the first thing out of the box are the TID complaints. So we ignore those. Let's go to below the last TID, which is right here. And we see stuff that I don't want it. There we go. It's complaining that, why does it keep doing that? It's complaining that it wants, that production wants to be given an expression pointer. It's complaining on 475, 6, 8, 9, 80. Let's take a look up here. 470. It's complaining about 475, 6. 5, 6, 8, 9, 0. So 5, 6. It's not complaining about this one, which is good. 8, 9, 0. We need to silence it. And so we know that here that this is, we can just do this. Right, a valid expression pointer is a null pointer. It doesn't know what t paren is. If you recall, the default on all these is $$ equals $1. It doesn't know what t paren is. It's certainly not an expression pointer. So that's why we're getting errors on all these. None of these we've said are expression pointers. So what we will do is we will just simply do this, and then we put that in a nice big comment, because your project isn't complete until you've changed everything that says change. This is just to let us get through the beginning here. So I'll just go ahead and add that to these. I guess I can add it here. Although it wasn't complaining about it, I probably would have been fine leaving it for the moment. All right. Let's go back. Let's try again. Make. Look at the beginning. We can see the first error, the first warning is about TID, so we're good with ignoring that. And then, whoops. There's the last TID. So now we're getting, it doesn't know what expression is. So this is just a pound include problem. And where do we put all of our header files? Our pound include statements? GPL.y, we sometimes run into problems because of the way GPL.y, the way Bison is generating the header file with the code it generates. So to get around that, we go into parser.h, and we just go ahead and do that. Let's try it again. Make our warnings that we don't have to worry about. And then down here, it has the same problem with integer constant. This is just a rinse and repeat issue. Go back in here and add constant.h here. Make again. We've got our TID warnings we don't have to worry about up there. This is a TID here, and it looks like we're off to the races. Okay, that's fine. I can run it, but I shouldn't expect anything exciting. We got the same thing. We still haven't resolved the root of the issue, but we're getting there. All right, so our integer constant is being assigned to $, which is primary expression. Where does primary expression go? It becomes an expression. Let me go ahead and be explicit about this. If I'm not, I'd have to resolve it a little bit later. My primary expression is being assigned to $. What do you predict is going to happen as far as errors? It is not going to know the type of expression. Let's have a look. Make. I look up above here. Before we ever hit the TID warnings, we have it right there. Is of no declared type. So this is your clue, this phrasing, no declared type. That immediately implies you need some sort of % type up near the top of the gpl.y file. So we come up to the top of the file. I search for % type, and expression is going to have an expression pointer. Come back down. Let's recompile. Okay, it's compiling away. Let me look up a little higher real quick. TID is my first warning, so I'm not worried about up top. Let's look down below the TIDs. And we have 448, 467, 468, 469. I'm sorry, 448 is a TID. I ignore that. All right, 467, 68, 69. Let's look at those. 467, 8, 9. So we said that expression was an expression pointer. If you recall, all of these default to this, right? Which is good. An expression can be assigned to an expression. It's not correct, but it's not giving us errors because it's just taking $1 for all of these and assigning it as the result of executing this rule. It's complaining about 7, 8, and 9 because $1 is not expression. It's something it hasn't seen before. So we can get around that. We'll just say $$ equals null pointer. Change this. Do it there. We'll do it there. Really, it'd probably be good if I did it to all of them. I'm going to need to change all of these at some point, so I may as well do that. Whether you did or not, it doesn't particularly matter at this point. So right now, the only valid expression is that primary expression that's coming from our hard-coded tint constant. So let me do a quick make again, make sure everything's going fine. Got the warnings up top, and it looks like we're compiling after the last TID, so we're in good shape again. We're still not quite there yet. We have to keep following this. Let's go back down the other direction, because I've hit expression going from smallest to largest. Let's start at largest again. If you recall, optional initializer. An optional initializer can be an equal sign and an expression. So this is where it meets up. All right, our tint constant object is going to hit this line on 266. So what should be our action here? Yep, that's it. We're going to have the same, right? Let's go ahead and avoid seeing that error again. We know that we're going to need a type for that. So I look for %type. I'll do a copy and a paste, and what I'll do is I will put optional initializer here. We know we're going to need that. And then hopefully this make will be rather happy. Not quite. It's happy down below, but up above here. So here's before the TID warnings. What's this complaining about? It's saying that the empty rule on 268, it wants an expression pointer, but it doesn't know what empty is. So let's look at that on 268. What is that rule? Let me go up here. It's saying that it can be either an equal sign and an expression, in this case our hard-coded number, or it can be empty. Right, if you write int a semicolon, that's an example of this optional initializer being empty, right? So the question is, what is something that you believe makes sense to put here if there is no optional, if there is no initializer? Yeah, $$ equals null pointer. Okay. All right, that takes that. Whoops. That goes ahead and that runs us all the way up here. So now we have an expression pointer right here. So let's look at our code. Here's our integer. I guess I could do this. What is that equal to? Or let me actually put it up higher. So I am creating a variable to hold on to our expression pointer. Where do I find our expression pointer? Yep. And then now I am ready. I need to turn this into a constant pointer because I need to get that constant value. How do I turn it into a constant pointer? That's a pointer, so I'll use an arrow. Evaluate. That is going to get us a constant pointer. I'll call this CPTR equals. Yeah, everyone buy that? All right. So how do I get the actual integer from my constant pointer? CPTR, arrow. Let's look at constant.h. Yeah, we eventually have to do some error handling, but at the moment, well, let's go with the case where we aren't messing with GPL. So I can create value, or excuse me, integer value. Value is equal to that constant pointer as an integer. Right, so we've got all sorts of interesting things we're about to have to work through. But this 42 now changes and is value. Let's try making it. I actually get an error from this. Let's look at that error real quick. Yep. Should get it. Why didn't I get it? Oh. Did I write that? I should have gotten that error. Let me see. What am I doing here? Why am I not getting an error? That is definitely problematic. No, let's roll with it. It'll come back at some point, unless it's up above. No. All right. Let's find my, let me clear the screen. Let me find my little printf statement. Printf. Now let's do the other version of it. Let me clear the screen. There's a question. Okay, so let's just run it. All right. I get a seg fault. The reason I'm getting a seg fault is because if my optional initializer is empty, we set $3 to a null pointer. So what we're doing is we're assigning a null pointer to EPTR, and now we're trying to do an operation on a null pointer, and that's where we're seg faulting, is right here. So how should I solve that? I guess what I could do is, everyone familiar with the ternary operator? I could do e pointer equals null pointer. If it is equal to a null pointer, then I'll just assign a null pointer here. Otherwise, I'll evaluate and get a constant pointer. So CPTR will either contain a null pointer or it will contain a constant pointer. This just saves us from writing an if statement there. Basically, have to do the same thing here. If CPTR is equal to a null pointer, now if it is not equal to a null pointer, we go ahead and evaluate it as an integer. But what if it is equal to a null pointer? We need to know what the default is. And for that, we can go to our GPL resources and look at the GPL manual. And right here, it says that integer, double, string, they all have default values. So 0, 0.0, or an empty string. Okay, so 0 is the default. Let's try it. Make. Nothing above the warning here, nothing below the warning here. Looks like we're compiling okay. Then clear the screen. There's the 0 if I don't provide an initializer. If I do provide an initializer, I get it. All right, so we've got that done for integer. Let's go ahead and erase through a little bit more of this. Let's go down to our t-int constant. And let's add these down here. So this would be new double constant, $1. And this would be new string constant, $1. Let's go back up to that whole optional. That's a nice hook to quickly find where I was. We had double val. Is a string constant a pointer? Let's look at constant.h. The string constant is not a pointer, it's an actual string. Oh, t-string constant, yes, yes, yes. So let's go to t-string constant, and that should be what? Yeah, good, good. And then delete. We don't need it any longer, so don't forget to delete it. All right, that was in there before I erased it with my recent edit. Oops, that's what I wanted. All right. Double val. Let me see. I could probably do a little copy and paste here. As double. The default is, that'd be fine, but I'll go ahead and be explicit about it. Let me see, 2yy, put, whoops, I got too many. Put, this is string, as string, val, and then this would be an empty string. Let's compile it. Nothing before the TID warnings. We do get that after, so let's get to the bottom of this. All right. It's giving me, it's saying redeclaration errors. Basically, to resolve all these it's best just to surround all these in curly braces. I'm not sure why the compiler isn't complaining about jumping into it. It might be. I wonder if that's something new with that 17 standard. Okay, let's try that again. Clear. Let me throw a few more of those in there. Make. Nothing before. Afterwards. Looks like that's going to come together okay. String x equals Bobby. And there we go. And let's try the default case. What did I do? Oh, I've got an equal sign in there. And there's the empty string. Okay. Now, let's see. I'm never going to get as far as I want to get. There's more that I want to do here because we haven't dealt with errors. For instance, if I say that, again, int x equals 3.14, that should generate an error because we can't assign a double in there. If you recall, what's going to happen is here I'll be asking for 3.14 as an integer, but that double object is going to where's my double? Here's my double object. It's going to, when I ask for a double as an integer, it's going to throw an exception. Now we can see that. I haven't fixed it yet. Let me start you on the strategy for fixing it yourself before I move to the binary operator. Let me try doing it. You can see right here that it threw an exception, right? The question is, well, what should GPL do? And for this, what you need to do is look at one of the executables I provided of the full working GPL interpreter. So if I run this instead, let me clear the screen. If I run this instead through, and I've got a copy of it right here, then I get this error. So what you need to do is around this bit here, you need a try block. And if it throws an exception, then what you need to do is generate this error. And where am I going to find which error this is? So we kind of remember it looks, when we actually get down to writing the code, somewhere in here in a catch block, we're going to have like, I can't even remember exactly what it is, right? You just have to find one somewhere else and copy and paste. But here we have something that's all in quotes. So how am I going to find that? Error.cpp. So let me. And what I can search for, like this bit here, for initial value of variable. And there it is. So it's invalid type for initial value. That's what I need to throw into that error message. You'll note it takes three things. So you just need to see, okay, one of them is going to be the type it tried to be, or the type of the actual initializer. How do you figure out the type of the actual initializer? It wasn't an integer. The clue is That's what it throws. It tells you what it is, right? So there's your information on that. But it's throwing me this GPL type. How do I convert GPL type to DOUBLE in lowercase? There's that utility function that converts GPL type to string, right? So you grab what's thrown here, you run it through that GPL type to string. That's the first one. The second one is X. Where does X come from? Oops, I'm not in the right one. That's this. Yeah, that's X. And then where does the int come from? Well, hell, you know it's an int because you're in this. So you can just write, is that part of the error message? You just do that, right? So you 100% of the time know it fell into that branch and it was trying to be an integer. So that's how you go ahead and resolve that kind of stuff in here, is you run it against the running interpreter to see what messages it produces. Now, with the remaining time, let's see how far we can get here with the binary operator. All right. First, let me look at expression.cpp, or let me look at expression.h. All right. What every single binary operator has, by definition, is a left side and a right side. So we see in the abstract base class, there on lines 22 and 23, there have been two expression pointers provided. Because again, we don't know where in the tree we are, right? It could be pointing to a constant integer 4, or it could be pointing to a whole other branch of the tree. We know that they all have in common the expression pointer, so that's the type of our left-hand side and our right-hand side. I note on line 21, I indicated that that data is protected. What that means is that derived classes are able to access that data. That's all that means. Otherwise, it's similar to private in that those outside the classes can't access them. But our derived classes can. So our plus class that's been created here is able to use LHS and RHS. And we have a constructor here that takes the left-hand side and the right-hand side, and then we have an evaluate function. So first, let's look at how to construct it when we're up here. I guess what I want to do is I want to go here, and then here. Let me bring that up. All right. So here's our constructor. Left-hand side, right-hand side is what's provided. We did primary expression, right? Primary expression came out of this down here when we had a t constant integer, or a double or a string. So not only can an expression come from a primary expression, it can also come from an expression, a plus sign. How do I know it's a plus sign? So if I go back to gpl.l and I look for t plus, we see that if a plus sign has been found, it will return t plus. So I know it's a plus sign. So this is adding two expressions together. I want to create a new plus object. And it takes two expressions, the left-hand side and the right-hand side. What are the left and right? There you go. That'll create it. It will traipse all the way up in the same way that our constant integer or constant double traipsed all the way up till we hit that optional initializer. And then, let me go back up to our optional initializer. So we'll get the table handler, we have a little error checking there. Here it will get that plus. And here we'll ask it to evaluate. Remember, every expression has an evaluate function, including plus has this evaluate function. But we have to write the evaluate function. So let's write it. Okay, right now it's just got to, I'll leave that there, we'll get rid of it at the end. We have an LHS and an RHS. What do you want to do with these? Evaluate. What do they create? Semicolons. All right, that's the first step. Now I am guaranteed to have two constants. Assuming that there aren't any problems, everything's going to go fine. Let's assume they're integers. And what are we going to do with them? Add them together. All right, so here's the question. Now on line 20, if I had a 3 plus 4, I do have 7 on line 20. But I'm not returning an integer on line 15. I'm returning a pointer to a constant. So what do I have to do? Make a new one. Absolutely. Now here's where I'm going to help you out with the memory management. It gets a little bit hairy on all this. If I look at expression.h, the base class all the way up for expression, I've created this variable. Note it's protected so derived classes can see it. This is called the evaluated constant. So this plus is creating this new variable. The easiest way to get things to automatically clean up is this new variable we create, we assign to evaluated constant. So I say evaluated constant equals, and then what I return, whoops, I already said return. So I'm returning that constant pointer. Really, if I wasn't concerned about memory, I could do something like this, right? But I am concerned about memory, so I'm putting this here. Why am I doing this assignment? What does that actually buy me? Eventually, everything's going to destroy, and when your plus sign destroys, it'll run this code up here, and it will release it. So that is a nice way of automatically cleaning up everything. So to make this whole thing work, you'll have to remember for all of your binary operators and unary operators, whenever you create a brand new constant dynamically, just assign it to evaluated constant. Okay.
Does that happen already in the constant class? Like a constant integer?
It does not happen in the constant integer because of this mechanism here.
How do those just believe it? Do we need to believe it?
They end up, well, let me see. I'm pretty sure they're not deleted here. It's because I would have to think about it. It's been a while. It gets cleaned up. In the worst case, we'll have to do a delete in gpl.y, but I don't think so. I think it all comes out. It all comes. Yes. Constant dot h. There's nothing to clean. Well, there's the allocated constant. Yeah, it would be. All these are being cleaned up here, except for the constant integer that's defined down, and I'm not sure. I'm not going to give you an answer. I reserve the right to remain silent until after spring break when I can refresh my memory where that code goes. It does clean up in the wash, though. All right. No heck, let's try this. I think there might be enough there to try. Yeah, I mean, the whole thing's going to go over like a Christmas tree if we do anything out of the ordinary. but it's a starting point, right? So let me do make. My TID at the top, so I'm good. Looking down here, nothing below. It's all coming together. All right, clear the screen. Let me find my printf. Note that this is to that binary that is fully functional. I don't want that one. I want the one I just compiled. 3 plus 4. There you go. I do children's parties. Get my card. All right. The kids love this stuff. Can you tell her to be quiet? I'm not done yet. You'll get your cake afterwards. All right. So yes, let's use the remaining time to start looking at some divergent cases. What if where am I? I want to be on the top here. So I'm going to expression.cpp. Here's the beginnings of my evaluated constant. I'm going to get rid of that message. I'm going to change my code a little bit, and I'm going to actually put my return up here. And I'll leave that down there and deal with that later. All right. So if everything works, line 20 is great. I do the dynamic allocation, I assign it to that variable, and then I do a return of that new pointer, or that new constant pointer. It could go wrong, so let's put that in a try block. I want to get every single one. In my try block, I want to assume that, let me run this again, oops. Let me run this on the Vagrant GP Arch. Oh, I'm sorry, I didn't want an int. I wanted a double. So this is intuitively obvious, right? However, for our code, it isn't going to work so nicely because we aren't. I'm sorry, this thing wants me to quit. For our code, it is assuming everything's an integer, and that double, the 3.14, as soon as I say as int, it's going to throw an exception. So if this thing throws an exception, let's assume that we've got at least one double in there. So here, what we can try to do, and we'll put this in a try block, and I'll copy paste. Now, does this make sense in my example that this would work? 3.14 plus 4. What happens if you ask an integer to be given ask an integer to give itself as a double? There are no issues with that, right? Remember the implicit promotion just returns itself. So this is very similar to a set of chained if-elses, and so that we don't keep indenting, just as we do with if-elses, we kind of keep them at the same level. So maybe I'll do something like that. All right, but that may throw an exception. Focus. Missing a try. Yes, I am. That matches the try. Matches the catch. Let's see, this is, and do this, inner, do we need another one? Where am I? No, I'm good. So this is the outer catch. And this the outer try's already got a match right there. So I'll just call this outer. So until you get used to it, to help you marry up the curly braces there. And then somewhere down here I've got the function. Yes, it will not compile if there's not a catch to go with the try.
Is there a catch that corresponds to the
I'm sorry, go ahead. What's that?
Is there a catch that corresponds to the ask string section?
What I will do is, for the moment, I will assume that it's going to be fine. We actually end up having to make our code a little bit more sophisticated later on, but for the moment, that should work. So we assume it's an integer, and we give it a go at it. If something isn't an integer, it's going to throw an exception, so we immediately fall into this catch block where we're going to try again. We're going to assume they're both doubles. But if we said something like 3.14 equals Todd in quotes, or even 3.14 plus Todd, or 3 plus Todd, it's going to fall out to this last one, and we assume they're both strings, and either integers or doubles successfully evaluate as strings, and of course strings evaluate as strings, and it's legal to add two strings together. How do I know it's legal to add two strings together? Because I consult this GPL language reference, and it actually has the operators and what's legal for each one. So multiplication is only legal with integers and doubles. Division's only legal with integers or doubles. The modulus operator is only legal with integers. So you can imagine if you do the modulus and it throws an error because one of them's a double or a string, then you report an error and you go run the running interpreter to find what the error is. Yeah? So shall we try it? Oh man, I am out of time. What a drag. All right, well, we can try it. We should have enough time. Expected unqualified 30. Unless I'm off somewhere. Yes, I'm off somewhere. Inner try. Thank you. It's going to work. All right. Printf. That worked. Oh, that's a built-in one, damn it. All right. I did something wrong, and I'm out of time. I'll have to debug it. Yeah, I can't keep you here. So I'll debug it. I'll post the debugged version with the class notes. All right?